All right, all yours.
Yeah. Hi everyone, I'm Nimeesh. So today I'm going to be presenting about my project, which is prediction of occurrence of parametric role using AI-based methods. So I'll be sharing my progress on this project with you. So first I'll go over what parametric excitation is briefly. So parametric excitations are oscillations which are driven by periodically varying a parameter of the system. So this is a very non-intuitive kind of phenomena. So I'll give a small example to help you get an intuition. So everyone must have played on the swings in the childhood and tried doing this like without swinging, without putting your legs on the feet on the ground. And so you must have wondered how this happens. So this is basically a result of parametric excitation. So what you're doing here is changing the position of your legs and body such that the center of gravity changes, and your body acts like a pendulum, and changing the position of center of gravity changes the length of the pendulum. Now, doing this continuously uh, produces oscillations. Yeah. So now we'll look at how this happens in ships. So we all know that the roll natural frequent period of a ship depends on the GM, which is given by this, and one of the parts of this is BM, which is the second area moment of water plane area divided by the underwater volume. Now, when there is a wave passing uh, through the ship, due to the wave, the water plane area and the underwater area changes. Now, when the trough is at the midship, the underwater area is more, and when the crest is at midship, the underwater area is less than what it is at the calm water. Now, this variation in underwater area will cause a change in BM, and this causes a change in GM, which is a variation in our parameter of the system. So this is what causes parametric roll. Now there are certain conditions which have to be met for this to generate cause resonance. So these conditions are that the encounter frequency of the wave should be twice the roll natural frequency, and the wavelength should be approximately equal to the ship length, and the wave height should be greater than a certain critical value. The roll damping of the hull should be less. So there are certain hull geometries which are more susceptible to this phenomena. So this is a flat transom stall. Here you can see that the hull form is changing very drastically, both at the aft and forward. So this is a hull form of the KCS hull, and due to this drastic change, the underwater area changes, like as we seen in the previous slide. And this is the general cause of parametric resonance in ships. So any doubts till now?
No, you go ahead. We will take the questions at the end.
Okay. So yeah, I'm using a simulation tool called SimDyne, which was developed by some of the students in our department. So I've used this tool to simulate the KCS hull in regular and irregular waves. So this is one simulation. I've used a 6 meter regular wave with a period of 21 seconds. Now here you can see this is a head-on wave. So the uh, yeah, it comes head on, so angle of approach is 180 degrees. Now here you can see that the roll amplitude is very low. Right. Now I slightly change the time period. The wave height is same and the direction is same. Now you can see the roll increases exponentially and settles at a certain value. Now this is parametric resonance. So from this, can you guess approximate range for the natural roll period of the hull?
Excellent. Good audience interaction. Anyone?
9.25 will be half, right?
Sorry?
It will be half of this, right?
This won't be half. The frequency should be half. So
Oh, yeah. Sorry.
Double.
yeah. So the roll time period of natural time period of the hull will be around 37 to 38 seconds. Then yeah. So there's a simulation in irregular waves. I've used a John-Swab spectrum with a wave height of 8.5 meters and time period of 13.5 seconds. So here you can see that the roll amplitudes go almost up to 30, 32 degrees. Yeah, I've simulated it for 5,000 seconds. So what I'll be doing now is I'm going to use this simulation tool to simulate the roll time history, like the roll motion for various wave environments, and I'll use this data to develop my models. Like I'm yet to decide on the model architecture and all, so right now I'm focusing on getting the data. So I have to run multiple simulations, each simulation around 3 hours, and so various wave cases. So I'm thinking I've got this data from like experiment conduct. This is data from IACS, International Association of Classification Societies. So this is basically the wave heights and periods in the North Atlantic Sea, the probability of occurrence. So I'm going to pick a few cases from this and then simulate for those. Yes, so as I said, I'll be using SimDyn for simulating various cases and using that data to train my model. And then I'll be trying to experiment with different model architectures. That's it.
All right. Time for questions.
Yeah. Nimeesh, could you go to that table that you showed, wave heights and frequencies? Could you explain this once again?
This one, right?
Yeah, could you explain it once again? Get it completely.
Yeah, so these are the time periods of the wave, and these are the wave heights, and this tells the probability of a certain time period and wave height occurring. So they use a John-Swab spectrum. And
Okay, so for these heights and time periods, you'll be simulating for the case as well. It's
Yeah.
like,
yeah.
okay.
I guess the more interesting question is, how did this table come about?
Yes, so this is from experimental data that they gathered.
So how must this have been constructed? What would be the methodology through which this table must have come across?
So they must have gathered the wave elevation data over a large period of time, and then seen which, like, how many times a certain wave with this height and time period occurs.
Yeah. So I think what the answer is simply that the corner box you see, which is about 100,000, maybe 1 lakh. 1 lakh waves were observed, at least, right? If not more. Right? In 1 lakh waves, then they were looking at height to height measurement of the records. So they were trying to figure out what is the no, definitely 1 lakh, more than 1 lakh waves must have been observed. And what they're looking at is they're trying to find out from each wave record you will have a irregular wave elevation. So you will figure out what are the heights, right? And over a certain period of time, you will find that the heights will be in some range. They will not be exceeding certain ranges. So that is what we define as a C state, over which time period the wave's significant wave height does not vary significantly. It's kind of oxymoronic, but nevertheless, the significant wave height stays approximately constant, or the zero crossing period stays constant. And from that, you figure out what is the, what you call, you take the top 1/3 of the wave heights from there and you see average them, and then you get the significant wave height of that time period. So let's say you collect a 3-hour long time history. Then you get certain amount of wave heights, you average the top 1/3, you know what is the significant wave height, and you average the zero crossing periods, you get the zero crossing period from it. Okay, but here I think one thing which you must consider in your simulations is zero crossing period is not necessarily the same as peak period. There must be some relationship. So please find out that relationship and make sure to incorporate that when you run your simulations, because the SimDyne program will expect the peak period as the input, not the zero crossing period. Okay, this is the only so the difference between them is very subtle, but nevertheless is there. You understand the difference between the two?
Yes, sir.
What is the difference between TZ and TP?
Zero crossing is the given wave elevations, how many times it is crossing the zero amplitude, and
Not how many times.
yeah.
You are taking each time it crosses across the zero wave height level. The wave elevation crosses zero between two consecutive occurrences of zero. Not even two consecutive, two alternative zero crossings. That is the zero crossing period. When it crosses in the same direction.
Okay.
From bottom to top, again when it crosses from bottom to top.
Okay.
That is zero crossing period. All such periods which you observe in a wave record, you will average them. That average is TZ.
Okay.
Okay, but TP is different. What is TP?
TP would be I'm not sure. Like,
TP is the peak period, which means if I took all the wave elevations, zero crossing periods, and I plotted a histogram of it.
okay.
Okay, suppose I created a spectrum of the wave elevation. Sorry, not the histogram. Sorry, it's not a histogram. It is the power spectral density of the wave elevation.
Yeah. Then the period of the maximum wavelength.
The highest point in that spectrum will correspond to that.
Yeah. Okay.
Okay.
So these two need not be equal.
These two in
The zero
general
crossing.
should not be, in general will not be equal. There is some relationship which you can derive between them, assuming that the waves follow a Gaussian distribution.
Okay. Yeah.
Okay, I think I should let the others ask more questions and I'll come back a little bit later.
In the right hand side, there is a column of sum. So what does it indicate? I think it is how many times the operation is repeated for the observation.
Which one?
The sum column.
Yeah.
What does it say?
So
Exactly?
this is the value. So this is 100,000 observations, and this is the So they basically say that they have observed like 100,000 wave. What do you call? Yeah, basically 100,000 samples, and this is the probability of each instance occurring.
You can call it 100,000 C states.
C. Okay. Yeah.
Is it like in the second last column, the total sum is 1? So is it like they have tested it one time, or it is just a probability that it will occur once at a million or something? Chance.
No, so this means that the wave height of 16.5 across various periods will only occur once.
Okay, just
Once every
100,000.
1 lakh C states.
Yeah.
The probability of we observing a significant wave height of 16.5 meters is 1 in 1 lakh. Did that make sense, Shadam?
yes, sir. And sir, if the row column decide the height, wave height, so what does the first row indicate? That's the 1.5 and 2.5 just starting.
This is zero crossing time.
Yeah. Yeah.
So along the rows, he is changing the wave height. Significant wave height is changing along the rows. Along the columns, the zero crossing period is changing. So I can have a 10-meter high wave with 1.5 seconds, but very unlikely to find it in the sea.
So these are the experimental values which we have.
Correct. So this was constructed after taking a lot of experimental data into account in the North Atlantic region. And from that, they constructed this table that if I have observed, let's say 1 lakh sea states, and each sea state itself might be very long, 3 hours, 5 hours, longer, especially if it is larger zero crossing period, then you need to observe for longer amounts of time to get a converged statistics. Not each sea state lasts the same time. So for example, let's say there is a storm, then you might expect to see 10-meter waves with, let's say, about 12-second period. Okay? But these waves will only last for, say, 3 hours. The storm lasts for 3 hours. But then you may be looking at 3 meters wave with a period of, say, 6 seconds, which are going to be persistently there. So they will be observed for a much longer period of time.
So these are continuously taken. These heights and the wave breaking point are taken. The values are constantly updating. As I think.
No, this was taken. So this was a wave record was constructed for a very long time. So you constructed this time history. You measured the wave elevation over many days, many significant what you call probably many different seasons as well, and then you collected this data. And here we are only analyzing the statistics of that data. We are not even looking at each of the wave height itself. We're looking at average significant wave height, which is the average of the top 1/3 highest wave heights, which you observed in that record.
And so, what is the use of Simlin? What is this Simlin?
What is the use of significant wave height? Okay, who is going to answer this question?
Yeah, so basically this significant wave height and the time period are used in like generating a wave spectrum of using different formulas. So one of them is the John swab. So basically this takes as input the significant wave height and the time period and gives a spectrum.
No, but why is significant wave height so important these days? Why are we looking at top 1/3? Why not look at the top half of the waves? Why the 1/3?
So we can take the average also.
Yeah, we can take the average. Why take the top 1/3 of the waves and average of those only should be considered?
To get high energy waves.
Come again, Ashwin?
To get high energy waves.
To get high,
Energy waves.
to get high
Like,
energy waves.
yes.
I didn't quite follow you. You care to elaborate a little?
Like, yeah, most of the waves would be, the relevant waves would be in that range instead of half.
Most of the relevant waves would be.
In the top three-fourths, I mean, top one-fourth.
So what is the criteria for being relevant?
Sir, maybe it causes more excitation to the ship, sir. Like it causes more impact.
Yeah, they have more energy, at least that's what I understood.
Okay, but then why one third? Why not one half or
Yeah,
one
the
tenth?
top one-third will have the highest energy.
No, if I take
The,
top one fourth, they will have the higher energy.
So if we are encountering it on a ship, we may take the highest one for the max, what we can then maximize the strength or something.
No, no. The reason for why it is significant wave height is only the top one third of the wave heights. It's not out of the blue, and it has an anecdote with it. So back in the day, ships used to be sailing across the oceans. The sailors would basically stand on the deck and be looking at the waves, and then we'll be trying to figure out what is the wave height. And in general, when you look at a sea and you try to predict and make a prediction, generally that was found to be closer to the top one third average. So our prediction was not as good as we believed. Sailors would typically will come up with numbers which were more or less matching with the significant wave heights, which is why the significant wave height became the criteria for us. It was not that 1 by 3 was something of a magic number that we suddenly chose. Okay, but the 1 by 3 also has a magic relationship to your variance of the sea, which means if I took the entire wave elevation time history and I calculated the standard deviation, then what is the relationship between HS to sigma? Significant wave height is how many times? The standard deviation?
Three times, sir.
It is 4 times standard deviation. HS is 4 times sigma for a narrow banded sea. And usually waves are considered narrow banded. Now all of this information that we are discussing right now is a very exciting area in the area of wave statistics. There has been for a long time, we did not know what is the wave process look like. Today we know that the waves are generally following a Gaussian distribution, right? But we did not know that for a long time. And also here, not all waves will follow Gaussian distribution. We're talking about deep water waves. When we start looking at waves in the shallow water environment, their characteristic changes, their statistics are different.
Can't agree more.
Sorry?
I agree with you.
Yes, you should be able to explain this stuff because you've been reading about it.
Yes, sir.
Yes? So that is how the significant wave height came about, because the sailors would generally look at the sea back in the day when, because ships have been sailing for a long time before we came up with the math behind it, right? And at that time, when people would look at the sea and try to figure out what is the wave height, they would come up with a number. Waves are looking approximately 4 meters. It usually meant that the top one third of the waves were coming out to be 4 meters. It was not an exact science, but then that is what it was closer to, which is why we have stuck around with significant wave heights. Okay, which is the average of the top one third wave heights observed in the sea. Everybody with me?
Yes, sir.
Yes, sir.
All right. More questions. Good question, Shadab.
Like I wanted to ask, you will take say these green and yellow region conditions, for example, if they are more common, and then you will put them through Simden, and you will get those plots of TUSS role, right?
Yeah, basically the roll time history.
Yeah, and then what would be the uh, MLCU role in this?
So I'll use LSTM network or something like that and pass train using this data, and then again like validate and predict on this data.
Uh, like predict what?
So you are saying what kind of ML model I'll use, or
No, like the overall role of machine learning in this,
In your
understanding
project.
this. Yeah.
Yes.
right? So right now what I'm thinking is I'll use the roll time history. So basically, I'll give if the model is given say a time history of 50 seconds, like up to that point, will it be able to predict how the ship will roll for the next 10 or 20 seconds?
Okay. Like it will try to
Like
understand the
forecasting.
physics of the thing.
Yeah, physics. Something like that. So basically, it will try to forecast.
Now come again, Vallabh. It will try to forecast what did you say?
Yeah, I felt like it will try to emulate the physics of the system. Like
If you are giving it role history and trying to asking it to predict forward, I doubt it is predicting any physics. If you give it wave elevation and ask it to predict the role, then yes, you are asking it to emulate the physics in some sense, right? I would presume. But the more fundamental question which is pressing in your head, which you are afraid to ask, is why? Why should I do this? Isn't it?
yes, sir.
So please ask away.
Yeah, like if we have simmed in, then why LSTM and all that?
Okay, so basically, if you simulate it, it takes a very long time. So right now, there was one simulation, right? This. So this itself took me around 1 hour approximately. So when if you use an ML model, I'm hoping that it will be faster. Like we'll be able to get faster predictions.
I have a doubt.
Yeah.
Like we have previous simulations, right? Why can't we use that to solve this problem instead of like past data we can use, right? Like this kind of simulation to predict the model outcome.
No, I didn't get you. Like, can you come again?
Like what I'm saying is, in this slide you already have this predicted data, right? Like
Yeah.
previous simulations. We can use this graph to predict how the ship rolls or something, right? Why should we go for ML?
Yeah, but this is for a certain C state, and the probability of occurrence of the same C state again, like that is practically zero, right? So if the ship encounters the exact same C, then we can say that it will roll like this. But otherwise, we can't say that, right?
Okay. So we are using a different approach from this graph, like prediction.
No, no. This is the simulation. So what I'll be doing is I'll simulate it like this for many cases and use that data to train a model which can predict, like if I give only up to this point, like you can see that say only up to 1,000 seconds I'll give. So this is the roll motion of the ship until this point. Now I'll ask the model to predict it for the next 100 seconds, how the roll motion will be.
Okay.
But by then, this Parametric roll seems to occur right between 0 to
No,
1000.
that is just an example. I mean, can you even give till this
Okay,
point?
so if you give a time period between 0 to 500, say, so it will try to predict this roll motion between 500 or 1000, something like that. 500 to
Yeah,
1000.
I mean that window sizes is like
That
that
I understand.
depends
But
on model training. So
okay.
that
So
is a
what?
general idea.
No, what should be the window size? I think that's what the question is slowly boiling down towards.
Yeah.
Yeah,
Like
I
both
think
Anand and Manoranjan are asking you the same thing. What should be the window size? Go back one more slide to the regular wave case.
right.
The answer lies here.
Okay, so parametric roll like takes around 3 to 4 periods to develop. So if you use a window size of that length, say 3 to 4 roll natural periods, and it is able to see the data in that, then yeah, so it should be able to predict after that how it happens.
So in this particular example, I see that you are at 5 degrees roll at about 200 seconds amplitude, maybe,
Yes.
roughly. And then 4 cycles down the line, if I go, you're at about 10 degrees amplitude,
Yes.
right? But if I go another 4 cycles, I'm kind of close to maybe 15 degrees.
15 degrees.
So the increase seems to be linear here, right? Why is the increase linear?
Why is it?
Because it seems that when we were discussing about parametric roll, or at least when you were presenting, we had the idea that it rises exponentially. So why does it rise linearly here?
Okay, I did not observe that.
Sorry?
I'm not sure, sir.
So, okay, maybe I'll ask you this. What is happening at 600 seconds?
It is going into a steady state.
So why is it going into a steady state? What is causing it to stabilize? Why didn't it stabilize at 200 seconds?
Because of the roll damping. Like as the roll increases, the roll velocity will increase, and that will increase the quadratic damping. So that is causing it to stabilize.
Correct. So it is the quadratic roll damping which is causing it to stabilize. And the answer lies hidden that if the quadratic damping was absent, you would not see a straight line increase.
Yeah.
See an exponential rise in amplitude. This is stabilizing. You are seeing that the amplitude increases from 5 degrees to 10 degrees linearly because of the presence of quadratic damping.
Quadratic damping.
If quadratic damping was not there, then you can try simulating and see within 4 cycles it will exponentially increase.
Okay.
Maybe that is something which you can check out, Nimeesh. I think it is worth the effort to check that out.
Yes, sir.
To understand the physics behind it.
Okay.
So in that sense, you have to look at 4 cycles or 5 cycles and then try to predict it. But then maybe more interesting problems can come across. Any other questions before I come up with some more questions for Nimeesh?
Sorry. Yeah, Krishna, will you go ahead?
Yeah.
Why you are choosing the chance of
Sorry?
why you are choosing the chance of wave spectrum? Why you are not
Mansi? I think she's trying to switch her microphone if I'm not wrong.
Yes, sir. So Krishna was speaking, so I thought he can ask a question first.
No, you can go ahead. Go ahead,
Okay.
ask your question.
Yeah, so just wanted to understand that in terms of predictions, you were saying that we can predict it for the next 15-20 seconds, right? Like the role, how the parametric role would be. But how does it apply to ships? Like, can you actually do something physically to the ship by steering it in certain direction so it can
Uh,
like stop it from
can you
weakening? So,
talk a little loud? Losing your voice.
right. Am I audible now?
Yeah.
Yeah, so what I was asking was that you said that we can predict it for the next 15-20 seconds, what the parametric role would be like. So I
Yeah.
just wanted to understand, like when you apply this to an actual ship, how would it translate? So if you know that, okay, in next 15-20 seconds, the ship is going to have this kind of a parametric role, so how does it get corrected? Because 15-20 seconds seems like a very short duration of time. So is it being applied anywhere else at the moment?
So what can you do with that information in a sense? Let's say I tell you that you're going to experience parametric roll in the next 40 seconds.
Right.
What can be done?
So here we have seen like the conditions which have to be met in order for the parametric roll to occur. So here we can take like maneuvers, the captain can take maneuvers such that these conditions are not met. So he can either change the direction of the ship or reduce or increase the uh, velocity of the ship. So that way he can try to avoid. So, and that is obviously provided he has enough time to make such maneuvers. So the prediction window has to be large enough that it is possible to do that.
Did that answer your question, Mansi?
Yeah, it did, but in a way it did. I understood that you can actually, once you know that this is going to happen, you can alter any of these four conditions. But like, I think what I also want to understand is 40 seconds even a time good enough to change your speed or even change the direction of the ship, because we're talking about really long ships here, right? So like, how are people solving this at the moment? Are people applying AI or ML techniques for solving this? Or would it be for autonomous vehicles and not for manually controlled ships?
So the question is, Nimeesh, that how are people solving it now without the use of ML? And why would ML help?
Okay, so currently they are using different methods, which looks at the what the what do you call it? The energy transfer, like something like the energy transfer between the heave and pitch motion into the roll motion. So I've not looked into it a lot. So their prediction window seems to be around 25 seconds to 30 seconds, if I'm not wrong. And so they say that those are the systems which are currently being used in ships, but they are effective to some part, but not very effective. Like recent papers, they like so like using these LSTMs and these models. So there was one paper which was able to show some good results in regular waves, which they used only multi-layer perceptron. And so I was hoping I can use better model LSTMs like that and able to see if it is able to perform well in irregular seas.
Okay, I think Nimesh, you want to answer the question, what happens when AI and ML were not there? There are traditional methodologies also to predict the occurrence of parametric role. Okay, and you've taken a look at least one or two papers on the direction.
Yes.
Right? So it only goes to show that you need to spend some more time with them to get a better understanding of what were the traditional approaches, what was the downside with the traditional approaches, and why the ML will be helpful. And I think I may have lost him. Nimeesh, are you there? Okay, I guess he must have had a power failure, looks like it. Okay, but I think Mansi, to answer your question, am I audible or is the network drop on my side?
Yes,
Yes,
sir.
no, sir, you are out.
Yes, sir, you're audible.
Okay, all right. So the primary idea is that what you can do in 40 seconds, you asked, right? And that's a very critical question. That's the major challenge when you face parametric excitation. What can I do in 40 seconds is a very tricky thing. But suppose you have U tanks, anti-roll U tanks installed on your ship. You don't want them to be in action unnecessarily because they drain out energy from you. But when you know that such a situation is going to happen, you can definitely get them ready into action in 40 seconds. Also, you can turn off your engines for 40 seconds. That will be a huge help because when you are going forward and then suddenly you reduce your speed, you change the encounter frequency of the waves which are coming at you. So since the frequency changes, that 2:1 ratio of the parametric resonance that is required, you're kind of altering that immediately. So these are certain things which you can take, the action can be taken quickly. If its effect might come slightly later, but at least it is not too late by the time you're starting to take the action. So you're not taking the action when the roll amplitude has reached 30 degrees and then you realize, oh my God, I'm in parametric excitation, but you're able to take it when it is at 5 degrees or much milder, and you know that in the next 40-second window you're going to experience it parametric excitation. I hope that makes some sense.
Yes, sir. It gives me a better picture.
Yeah, so that's the primary idea why you want to predict it over a shorter window. All right, any other thoughts, comments, questions?
Sir, I have a question. Am I audible? So, how is whatever approach Nimesh is gonna use for predicting the roll and every other motion? How is actually different from all these dynamic positioning system that exist right now, apart from the role of GPS? Because eventually they are also trying to keep that given vessel at a position, right? And Nimesh is also trying to maintain the course of a given vessel. So why can't we that extend those things into something what Nimesh is doing instead of doing it completely from scratch?
All right, Nimesh, are you back?
Yes, sir. I
You
lost
want
you.
to take that?
Can you hear me?
Yes, I can hear you.
Arati, can you repeat your question? It's breaking.
I asked all these dynamic positioning system exist already, and their task is also to keep that given vessel in that given position and and they also encounter all these parametric roles, even other motions. Why can't we extend their application into a ship motion thing instead of trying it from scratch?
So, right now I'm not looking at correcting or like stabilizing it. So, I'm just trying to see if the parametric role will occur. So, like, not all ships need may not have that what do you call stabilizing systems, right?
No, I think the answer to that is slightly different. And I'm hearing an echo from someone.
Hello.
Am I audible fine now? No, I think the echo is from you, Nimesh. Yeah, okay, all right. Okay, so I think the answer to that question is Aradhya, ship dynamic positioning systems usually try to position you in the horizontal modes. You want to keep it at a particular location in the XY plane, and you want to keep it orientation in a particular position in the heading angle to be a certain location. Typically, in ship dynamic positioning, you will not see where we want to control the sea-keeping modes. Because if we try to control the sea-keeping modes, then we are spending too much energy of our actuators. It just does not make much sense. We are using all of our thrust allocation to keep our sea-keeping motions down, whereas the sea-keeping motions are only vibratory in nature or oscillatory in nature. They are not going to be positioning us away, so they don't hinder the operation as much as the drift in the surge, sway, and yaw does. So most dynamic positioning systems that you come across, whether it be for offshore operations or whether it be for any other purposes, is usually looking at controlling the horizontal plane motions. So extension of those into the sea-keeping modes is a different ballgame, because whatever is happening in the horizontal plane is happening at a much lower time scale, so longer time scale. It all occurs over the what you call minutes, or sometimes few minutes, or less in seconds. That's what I wanted to say essentially. It takes more than a few seconds for your ship to move out of position in the horizontal plane. But whereas when you're looking at sea-keeping motions, most of those motions are in a order of a few seconds. Am I making sense?
Yes, sir.
Okay, and when they are in the order of a few seconds, when you want to control them, you really need to put in a lot of actuator control on it if you really wanted to control it actively. So usual approach would not be to try to bring stabilizer fins and do an active control, although that is possible, but usually not preferred for sea-keeping motions. A much better passive approach is much better here. I shut off my engines, my encounter frequency changes, I am away from my problem. That's a much easier approach, right?
Yeah, makes
Yes,
sense.
sir. Yes, sir.
Or I change my direction. I just apply a rudder, change my direction, and I wait for my ship to just start turning. And as it starts turning, the waves are no longer coming head on, they are coming at an angle. So now again the encounter frequency changes. It's a much better strategy to employ them rather than to apply active control where you know you are in parametric excitation. You want to be locked in that resonance, but try to actively diffuse it. It requires much more effort.
Yes, sir.
Okay, I hope that answered your question somewhat.
Yeah, it did.
Okay, all right. Any other queries? Nimesh, can you put up your presentation one more time, the irregular C case?
Yes, sir. One second.
Yeah. Here you are saying that the John-Swath spectrum, you're looking at 8.5 meter significant wave height and a peak period of 13.5 seconds, correct?
Yes, sir. Yes, sir.
I wonder why nobody asked you this question. Why at 13.5 seconds do you expect to see parametric excitation occurring? Your natural period of the vessel is 37 seconds.
Yes.
So which means 18 and a half seconds is where you're looking for the energy. Why with a peak period of 13.5 you're observing this?
So it can occur at what do you call it? Frequencies higher than of ratio 1:2 also. So need not be exactly at that ratio, but any frequency higher.
Any frequency higher?
Like,
are you sure?
Not very high, but somewhere close to that.
So what is that range looking like? Is there a bound on that range which we can make?
That I'm not sure.
Okay, you can make a bound on that, depending on how much damping you have in your system. If you have some amount of what you call good amount of linear damping, then that range will be smaller. The more the damping, the smaller will be that range of frequencies over which you will observe this phenomenon. And if the linear damping is very strong enough, you may not actually see a parametric excitation also. Okay, and this comes back to that idea of that in-phase strut diagrams which you were looking at in the beginning of your research. I think you want to kind of look back at that to make sure you understand this phenomenon correctly. I would guess that would be worth the effort.
Okay.
Okay. Now, the other question which I had is, one of the things which you mentioned was that suppose I have a wave elevation for 100 seconds or roll time history for 100 seconds, you are trying to predict for the next 40 seconds what happens. Something of that sort, right?
Yes.
But suppose I am looking at the wave elevation problem where I know the wave elevation history, or let's say I know the future what the wave elevation will look like, and I want to predict what is the parametric excitation, what is my roll angle which will come. Okay?
Yes, sir.
So if I wanted to do that, can I say that if I know a certain amount of wave elevation time history, I can predict all the way into the future?
You mean like the entire duration of the wave, or more than that?
Not the entire duration, but let's say that a C state, a particular C state that you're investigating prevails for, let's say, 3 hours.
Okay.
Okay. So suppose I give you 1,000-second time history of roll and time history of wave elevation.
Okay.
Can I predict what will be the wave elevation for the rest 9,000 seconds and also predict the wave motion for the 9,000 seconds if the C state remains constant?
But we have the C state for that 1,000 seconds.
Yeah, let's say that John Swab spectrum is the C state, and you know that exactly is 8.5 meters and 13.5 seconds.
Okay.
Okay, and I give you 1,000-second wave history. Can we predict 9,000 seconds what will follow?
Yes, sir. That should be possible.
How would we do that?
We would train the network with both the wave elevations and the roll history.
I'm not talking about the network here at all.
Okay.
I'm thinking from a physics perspective, without AI. Can we know what exactly will happen? And this is a generic question for many of you, okay? Because this is no longer particularly only related to parametric rho. In general, for ship motions, if I know that the significant wave height is 8.5 meters and the period is 13.5 seconds, and I give you 1,000-second time history, can I predict what will happen in the next 9,000 seconds? Anybody wants to take a jab at it?
What C state are we considering? Is it fixed for those 9,000 seconds also, or
Yes,
it
it's
will
fixed for
change?
those 9,000 seconds. I'll even simplify it. Let's take the peak period to be 10 seconds. Let's say wave height is 8.5 meters, peak period is 10 seconds. Can we get a good estimate? And if the answer is yes, how? And if not, why not? First of all, I want to make sure everybody got the question. Everybody has got the question?
Yes, sir.
Can you repeat it once?
Yes. The idea is I know that the C state in a current location is 8.5 meters significant wave height and peak period is 10 seconds. And I know that it follows the John Swap model. Okay, that is given to us. Now I give you a wave history of 1000 seconds. And I say, can you predict what will happen in the 9000 seconds? Can you predict it? And how will you predict it?
Okay, let's look at now.
Sir, like I'm thinking that say this is a statistical model, right? Then having this some for some time these the conditions, and for other time like adjusting such that the same statistics parameters hold. Even that would happen, and we can't know exactly. That's what I'm thinking.
Sorry, come again. I didn't follow you fully.
I think he's talking about like creating a time series type of stuff which follows the same statistical model as the first 1000 seconds, and then we'll shift our window slightly to predict for the ahead stuff. I guess that's what he's saying.
Like I'm saying that it won't be exact. Like the same, you can have the same statistics, but like on average, but different at different intervals, different actual
Yeah,
wave
of
heights
course,
and
it
all
will
that.
not be repeat of what I see in the 1000 seconds will not repeat itself in the next 9000 seconds. I am not
Like
saying it's going to repeat.
I'm also not saying, but like we want to predict based on just these, right? So
Yes, I only know 1000 seconds. I want to predict 9000 seconds.
yes, so that's what I'm feeling, that it might not necessarily be possible because of the same. We can generate different, uh, like totally different history, but it might have same uh, like statistics for the rest of the time.
So you are saying it is not possible.
Yeah, I'm feeling that it is not possible.
Okay, so it is not possible because the statistics
Sir.
may be same, but I don't know what the wave elevation will look like.
Sir, is this a random model?
Is this a
Random model?
Is this a random model meaning?
Are the wave elevations random according to these parameters?
I still did not follow the question.
I
Like
think either
how you generate the weights for some time history is by sampling across the spectrum, right?
Correct.
And you're randomly sampling across the spectrum. And if you're doing that, you do not have any idea.
No, but I already gave you one such sampling. I have given you the 1000 second history.
Yes, but that sampling is random.
Yes, I have sampled it randomly, but I have given you a 1000 second history from that sampling.
So we can do this like taking the 1000 second sample. We can predict just to suppose 10 second
Yeah,
minutes.
then
Now we
then
have
you can reconstruct.
1010 seconds of sample.
One
Just
second.
by
1 second. Shatab, you go first. I'll take Ashwin next. All right.
so we have 1000 seconds of data. So from this we can predict next 10 seconds, for example. And now we have 1010 seconds of data.
No.
So while using
How are we predicting the next 10 seconds?
we're using.
If you can predict the next 10 seconds, I can argue that you can predict the next 9,000 seconds. That is what is the question. How do I predict the next 10 seconds? Okay, Ashwin, what was your thought process?
Yeah. So what we have, we sampled across the spectrum. So what do we have?
I
What
gave you
sample?
the
We have
time.
frequency. We have a frequency set.
I only gave you the time history for 1,000 seconds.
Yeah. Can we calculate the frequency set from that of the individual waves?
Yeah, that's what is. You have to think about how to do that. No?
Okay.
Give
If
you
we can,
1,000
if we
seconds.
can, if we can do that, then we can reproduce it.
Yeah, I give you 1,000 seconds. Can you give me what will happen in the 9,000 seconds?
Sir,
We can do some kind of decomposition to the data set.
Decomposition can we do to achieve that?
sir,
But I forgot what it was called.
Okay, Anand.
sir, maybe, sir, we have a bunch of variables like frequency and damping and all, right, sir?
Mhm.
So for one particular time, for example, at 100 seconds, there's a particular roll degree, and for that
No,
roll
forget
degree,
about roll altogether. I gave you 1,000 second wave elevation time history. So don't even bring the dynamics in it. Forget the dynamics. We will even make the problem much simpler. You have a Johns-Fox spectrum, 8.5 meters significant wave height, wave peak period of 10 seconds. I give you 1,000 seconds of wave elevation. Can you tell me what is the 9,000 seconds afterwards? Forget that we are even considering the role at all in this. We have the wave elevation for 1,000 seconds. I know that the Johns-Fox spectrum is applicable here, 8.5 meters, peak period 10 seconds. I want to figure out what happens in the 9,000 seconds. How do I go about this?
Yes, sir. Yeah. So decomposition, can you apply the Fourier transforms?
Okay, we apply Fourier transform over what?
You get the you apply the Fourier transform to the wave elevation.
Okay.
You get your individual omegas.
Okay.
Then once you get the individual omegas, you can just superimpose individual waves across 10,000
Across
seconds.
10,000 seconds to get the 10,000 second period, right?
Yeah.
Bingo. Very good.
Okay.
Very good. That is how we will get the 10,000 second period. If I know that the wave's steady state is fixed and I know 1,000 second time history, then I know enough information about it in order to reconstruct the rest, however long a time history I want for that particular sample. Okay, why this does not work in the real field is what Vallabh was saying. That random seed which I have chosen, whenever we are applying a Fourier transform over a particular finite length signal, we are assuming that when I apply a Fourier transform over that finite length, that signal repeats at that length. Am I following? Are you following me?
yes, sir.
Okay, so the signal will repeat. And that is why when Ashwin says I will take the Fourier transform and combine those wave elevations and then I will perform an extraction for 10,000 seconds, what he will see is essentially a repeat of the 1,000 10 times.
Yeah, that's why I said in reality it should be random.
In reality, it will be random, but it will not come out because that finite time history that you have taken, it will repeat after the 1,000 second interval, even if you took the same Fourier transform and took the same Fourier frequencies. Is that sinking for everybody?
Yes, sir.
I know the question is anticlimactic, but I wanted to drive home a point here, where I wanted you to think a little bit about Fourier transforms and their applicability.
No, sir, I didn't understand this.
See, whenever, suppose I am taking a, maybe Nimeesh, you can stop sharing. And maybe I can share my screen. Let's see if I can do this. Is my screen visible?
Yes, sir.
All right. So let's say that I have a time history. Okay, so it looks something like that. Okay. And this is my wave elevation versus time. Okay, what I am saying, I am taking a particular amount of time up till which I have observed T1. So I know what is the wave elevation from 0 to T1. Yes?
Yes, sir, yes.
So when I take 0 to T1 and I take a Fourier transform of that, okay, I'll get, let's say, some function of omega. And when I plot this, I'll get some points like this.
Yes.
And probably that will be the maximum. I'll not get any more points than this. This will be my Nyquist frequency. That is the maximum frequency I can sample based on the time step that I have taken. What is the minimum time step dt? That will determine what will be my Nyquist frequency. I can't get any more frequency resolution than the Nyquist frequency. So I take these individual components. Ashwin is saying that I'll take these individual amplitudes that I have read off from the n of omega using a fast Fourier transform. And I'll simply construct this one is A1, this one is A2, and this one is A3, so on and so forth, corresponding to frequency omega 1, omega 2, omega 3, and so on. So what he's saying, I'll simply do A1 cos omega 1t plus A2 cos omega 2t, assuming all the amplitudes are real, otherwise you'll have to do the complex stuff. I'm just taking this for simplicity, okay? Omega 3t. Otherwise you would have to do actually A1 e to the power I omega 1t plus A2 e to the power I omega 2t plus A3 e to the power I omega 3t and so on, and take the real part of that. Okay, if A1, A2 and A3 are complex, which they usually will be. So we can forget about this aspect and we can stick with that. Now I can simply say that eta of t is equal to this, and I can plug t equal to 0 to 10,000. Yes?
This will be correct for 0 to 1000 seconds, but from 1000 to the remaining 9000 seconds, how it's
Correct. From 0 to 1000 seconds, it will give back the exact wave elevation time history that you have here.
Yes.
Right? But from 1000 seconds, so if this is 1000 seconds, from 1000 the signal will repeat again. It will look like this. And it'll do the same thing which it did before. Okay? It will not do whatever this is. This is not what you will get back. It is this one that you will get back.
Okay.
The reason why we can't reproduce it is because this, when we make the Fourier transform of a discrete time, we are assuming that the signal will be repetitive after 1000 seconds inherently when we construct this transform. Okay. This transform by definition assumes that eta of t is equal to eta of t plus 1000.
Okay, it assumes that the wave elevation is periodic with time period 1000.
Correct. That periodicity is assumed. In fact, these omega 1, omega 2, 3 and so on will be nothing but 2 pi by 1000. This one will be 4 pi by 1000 and so on and so forth. This will be 6 pi by 1000. It will go in increments of 2 pi by 1000. When you tip the transform, these frequencies that you will get will be in increments of 2 pi by 1000. Everybody with me so far?
Yes, sir.
Okay, so that is why the smallest period that you have here is 1000 seconds. The first frequency here, the fundamental frequency that you have here is 2 pi by 1000, which has a periodicity of 1000 seconds, which means this entire signal, since it is looking at higher frequencies which are multiples of this frequency, will definitely repeat in 1000 seconds. Yes, everybody with me?
Sorry, sir, can you repeat this again?
See, the first frequency here, when I calculated omega 1, what we are doing, we are simply expressing this as some Fourier series, right? Cosine of omega nt plus bn sine of omega nt. Some signal eta of t is now given by these, where omega n is n times delta omega. That is what is your frequency incremental step, right? Omega 1 being delta omega, which is 2 pi by 1000. Omega 2 is 2 times delta omega. Omega 3 is 3 times delta omega, so on and so forth, isn't it?
Yes.
That is how we construct Fourier series, isn't it?
Yes, sir, yes.
So therefore, the first frequency, which is 2 pi by 1000, has a period of 1000 seconds, which means the entire signal will definitely repeat in 1000 seconds. Yes?
Yes, yes, yes.
And that's the main reason why the Fourier transform will inherently have this assumption built into it when you took the FFT to construct this n of omega. You can't get back more information than what you had previously, even though you knew the statistics of the system. Okay?
Yes.
And here is where Ashwin's question was very important. Ashwin, what was your question? Do I know the decomposition? Isn't it?
Yes. I think
And would you care to elaborate how, if I knew the decomposition any better, how would that help?
Yeah, what we're missing here is the other individual frequencies not included in this time period.
Correct. We need more frequencies. If I know what the value is, somewhere in between, these values which we don't know, then if I already knew that ahead of time, in addition to my 1000-second time history, the 1000-second time history will only give me these discrete set of frequencies. But I need much finer resolution if I want to reconstruct a signal which is 10,000 seconds long and is not repeating itself. And that I don't have from the 1000-second time history. That information simply does not exist.
So that information we actually cannot have, like.
Correct. What I can do is I can make a prediction. See, once I get this curve, I don't want to erase that. Okay, yeah. So let's say I have this curve. I formulate a curve and I say I'll interpolate. I'll try to get these values in between. I can do that, isn't it?
Yeah.
But then when I take those values, I have to assign them some phase.
Yeah.
And when I assign them one phase, what I'm doing, I am specifically choosing one possible outcome out of many hundreds and thousands that could possibly happen. Which means this wave elevation need not go like this. It could have gone some other way as well. And that would still be valid.
Yes.
So there are multiple possible ways I could come up with a new wave elevation which matches my 1000-second time history, but at the same time also has a extension. But that is not known for sure. I have multiple solutions. I don't know which one it is going to follow. Okay?
Yes, sir.
That is what is the idea I wanted to drive home with that example. I hope that made some sense. If not, I am really hopeful you will ask me and tell me that I did not understand. Yes, everybody with me?
Yes, sir.
Okay, excellent. All right, so I think any more questions for Nimeesh? No more questions? All right, so then we'll stop recording.